This project is focused on the frequency domain modeling, simulation, and validation of a single-phase AC power delivery system for industrial facilities. It aims to maintain the precise voltage regulation and high power factors to ensure optimal efficiency and machinery reliability. It implements fundamental AC circuit theories such as nodal and mesh analysis, superposition, source transformation, and Thevenin or Norton equivalence to solve complex electrical parameters. Cross-examines and validates analytical findings using the full-set circuit simulator to evaluate percentage deviation and assess the structural reliability of the framework.
Let me explain the background of our project. This project focuses on the semi-remote industrial facility that operates using a dual supply AC network. That systems consist of the primary utility power source and the secondary investor-based backup supplier to ensure continuously operation. The facility drives a small induction motor load through the transmission line with a specific impedance. The line impedance is Z1 equal to 3 plus J7 omega, while the load impedance is Z2 equal to 5 plus J3 omega. However, the system experienced several power quality issues, these including voltage fluctuation, voltage drop, specific phase shift, and low lagging power factor. These problems are merely caused by the reactive components of the load and the transmission line impedance. As a result, the systems may become unable and less efficient. In several cases, their conditions can lead to explosive thermal displacement, overheated, and possible damage to electrical equipment. Therefore, the main objective of this project to analyze these electrical variations, evaluate their impact on the system performance, and identify solutions that can improve stability, efficiency, and equipment protection. Thank you.
Now we go on to the simulation step. Firstly, the image shows an electrical network being modeled in a real-time circuit simulator, FALSTAT. This software is used to visually validate the mathematical calculation and test how the circuit behave under specific condition. Okay, next, the schematic display a multi-loop AC circuit featuring two distinct alternating current power source, left and right. These sources are feeding a central electrical load through lines and contain both resistor and inductance or coil. Okay, lastly, we go to the graph at the bottom. Act like a virtual oscilloscope, which is they display the fluctuating sine wave of the AC system, providing the real-time measurement of key parameters like current, voltage drop, and power consumption across specific components in the central load. That's all.
Moving on to slide 6, which covers our simulation, validation, and comparative analysis. As you can see from the comparison table, our manual analytical derivation and the FALSTAT simulation data is highly distinct value, resulting in a very large percentage error, particularly within the power parameters, which scale up to 650.8%. As a future engineer, our group chose to look deeper into this phenomenon rather than treating it as a flawed setup or a critical failure. The true technical reason for this extreme deviation is the systematic difference between our analysis domain. Our manual analytical calculation rely on the static phasor domain using Cramer rule, where the 90-degree phase angle of source 2 is calculated strictly as a static complex operator. On the other hand, the FALSTAT simulator operates in the dynamic time domain, executing real-time numerical integrations based on live wave force over under a 90 degrees temporal offset. Because power parameters are evaluated through quadratic equation, specifically P equal to I square R and Q equal to I square XL, any small phase shift variation in real-time current, wave integration automatically magnifies the final percentage error exponentially. Therefore, we can confidently conclude that both our theoretical formulas and our simulation configuration are structurally correct. They simply represent different dimensions of tracking alternating current system. Moving on to slide 7, let's look at the engineering interpretation of our system performance. First, a several voltage drops occur across the network. This is primarily driven by the high transmission line reactive impedance acting against our industrial load. Second, due to the inductive motor load, the system operates a poor lagging power factor of 0.496 to 0.598. This forces the network to spend a massive 1,369.21 VAR purely on non-active reactive power rather than delivering useful real power. Third, running an industrial motor under this heavily depressed voltage level poses critical structural dangers. It can cause systematic starting failure, several internal overheating, and eventual installation breakdown. Finally, this dynamic deviation highlights why transient-capable software is absolutely crucial in real-world engineering. It allows us to accurately capture real-time dynamic phase shift and practical reactive loss that static hand calculation simply cannot show.
In conclusion, I want to say our tests show that heavy load on motor make the voltage and efficiency drop. This means the system losing a lot of energy. To fix this problem, we recommend adding capacitor bank next to the motor. We will balance the power, and this solution will give us great result. First, it improves the power factor to 0.95. Second, it lowers the stress on the power line. Third, it brings the voltage back to the normal 240. Finally, it reduces the energy losing.